When you're working on these two-dimensional problems, one thing that's extremely important, in fact, rarely were a problem we worked without some sort of consideration for the hang time, which refers to how long an object is in the air. So a couple of considerations about where this hang time comes from. Here's a basic example here where you might launch a projectile like this, two-dimensional motion. You might give it some initial speed at some angle like that, and it'll sort of make this parabola, which everyone is familiar with here. And a lot of questions could be asked about this. In particular, one might be, how far does it go? Sometimes it's called the range. And the range is going to come also directly from, say, some delta t sub h. I'm going to call it the hang time. How long was this projectile in the air? So from the time it launched, if you started calculating alligator 1, alligator 2, alligator 3, alligator 4, and then slammed into the ground, that would be delta t sub h, the hang time. Now this is the simple case here where the ground, the launch position, and the landing position are at exactly the same level, but you could have other cases as well. Suppose you had a problem like this, where you launch the projectile from the top of a building, something like this. Now here's the V naught, and there's the theta in there. You will still get the projectile motion, but it's very asymmetric now. Nonetheless, this object still has some delta t sub h. It still has a hang time. How long was it in the air? So all right, it leaves the top of the building. Alligator 1, alligator 2, alligator 3, then bam, it hits the ground there. It's also going to have some hang time. As you might guess, if it was launched from some height above the ground, that's definitely going to affect the hang time. Here's another type of problem, where suppose it's just the opposite of that one here. Suppose the ground's here and there's a tall building like that, and you're going to launch a projectile like this. Again, here's some theta, here's some V naught, off it goes. Alligator 1, alligator 2, alligator 3, like that. This also has some hang time, how long it was in the air. Sure, it started from the ground and landed on top of a building, but it still had some time in which it wasn't touching either the ground or the building, and that's, of course, classified as a hang time. So there's all kinds of considerations like that. So when you hit these two-dimensional problems, often by looking at the hang time, you'll get clues about how to solve the problem. Let me show you where that comes from now. It turns out that the hang time, if I just can erase some of these examples right here and go back to the original title here, the hang time always comes from looking at the y-coordinate only. The y-coordinate only. There's no consideration with the x at all. So you look at what's going on in the y-coordinate or the vertical component. That's where the hang time comes from. So what sort of considerations do we have? Well, let's just go ahead and then look at the case here. We'll look at two examples here. We'll look at the case where the projectile is launched from the ground. There's the V naught and the theta, and it sort of does something like this. Okay, so the y-coordinate only. Well, what we know about the y-coordinate then is that y is equal to y0 and plus v0 times the sine of theta delta t minus 1/2 g delta t squared. This is the equation that governs how a projectile flies through the air in the vertical sense. And notice that the v naught sine theta, this part right here, is the initial the initial y component of the object's velocity, v naught times the sine of theta. So how would you figure the hang time in this? Well, we know that the initial or current position of the object when it's being launched in the y direction is 0 because it's starting at ground 0. And we know when it flies through the air like this, it's going to end up at 0 also. So both the final and the current or initial positions of this ball are 0 because it's landing and being launched from the ground. If we continue on with the equation here, we'll see it's v naught times the sine of theta times delta t minus 1/2 g delta t squared. So we get this little equation now, which it looks like we could solve this for delta t, get an answer for that. And this will be delta t some hang time. You can get the hang time of the ball from that analysis there. So here's the two zeros. And if you just take a few steps on this equation right here, it looks like a simple algebraic one. One of the delta t's will cancel, and you can get a delta t which represents the hang time of the ball from that simple launch condition. But it isn't always that simple. But even when it's not that simple, the analysis will still be the same. Let me show you another example, getting the hang time. Here's the ground once again. Suppose you had a ball that's launched from a building like this. And the building is a height h above the ground. So the launch condition looks the same. There's a v naught and there's a theta, and that's the motion you'd expect it to have. So again, the question is, what is the delta t hang time of this projectile? How long is it in the air? Same consideration. Y is equal to y naught plus v naught times the sine of theta delta t minus 1/2 g delta t squared. Same equation governs the motion, even though it's greatly asymmetric now. Launched from a building, not the ground anymore. But now we just start interpreting the signal, the symbols in here. The final height is where the object actually hits the ground. That's going to be 0 again, just like in the last example. Now it's not launched from 0, it's launched from a height h above the ground, so there's your h. And we're still going to have the v naught times the sine of theta times the delta t minus the 1/2 g delta t squared. Now if you look very carefully at this, the claim is that you can still solve this for delta t. You can still get a number for delta t, and just like last time, this is going to be the hang time of the ball. You can still get that. But the problem with this equation, this comes up a lot now in these types of problems, is that if you look very carefully, this is a quadratic equation. A quadratic equation. And that gives students a lot of trouble, but you need to get yourself ready, you need to get yourself set and have some plan for how are you going to get this quadratic equation solved. So in particular, if I just sort of rearrange the equation a bit here, I'll get minus 1/2 g delta t squared plus v naught times the sine of theta delta t plus h is equal to 0. Just a little bit of rearrangement of the terms there. And if you look very carefully at this now, you can see that the variable is clearly delta t. There's a delta t there, there's a delta t there, and there's no delta t there. So in terms of the quadratic equation and things you might be familiar with, the quadratic equation is always something like ax squared plus bx plus c is equal to 0. And you can use the quadratic formula to solve this now, but if you look very carefully, a is always going to be the minus 1/2 g term. B is always going to be v naught times the sine of theta, and c is going to be the height of the building. So you still can get the hang time of the ball, but it's a little bit more complicated now. It's not a straight linear equation the way it was when the landing and launch positions were the same. So it's very important that you sort of have this ready to go and you're familiar with the procedure. You know how to solve quadratics, and even that you know why it's a quadratic. And if you look very carefully, how did the quadratic equation come up? Well, it's because of this h sitting here. When y and y naught were both 0, it made the equation extremely simple. But when you have an h here, in other words, you have a launch condition which is not the same as the landing condition or the landing height, then you will have a quadratic equation. And notice the same thing happens if it's launched from the ground, say, onto the higher spot on the building or something like that. So you can have a condition like this, where there's a high building up here, and say the building has a height h like that, and you're launching like this. So there's your v naught and there's your theta, and say you have some expectation that the ball is going to make it to the top of the building. Once again, if you fill in that equation for the y coordinate of the system, you see, okay, it's going to end up on top of the building. It's going to start at ground level. It still has the v naught times the sine of theta delta t. That still is the y component of velocity there. And you still have the minus 1/2 g delta t squared term. So once again, you have a quadratic equation. There's a right there. There's b right there. C is now, looks like it could be 0, but if you move the h over, you'll get 0 is equal to minus h plus v naught times the sine of theta delta t minus 1/2 g times delta t squared. So now there's your quadratic equation. There's your a, there's your b, there's your c, which is now negative h, not positive h. But in either case, you should still be able to solve this for delta t and get the hang time. Actually, you'll just solve for delta t, and what you'll get here is delta t, which will be the hang time. So you can also get how long this ball is in the air being launched from a condition like that. And there's all sorts of other types of problems which can pop up, which you need to be ready for, but our theme is still the same. The hang time always comes from the y coordinate only by looking at the vertical. So no matter what the problem is, you can always identify where it was launched from, where it's going to land, and whether it's a quadratic or not, you should be able to determine the hang time of the ball. Here's one more example here. Say an object that is launched like this. Say it goes all the way down into a canyon like this. And say the launch is even very simple. Say it's just dropped like this from a height h. What would the hang time of this particular problem be? Well, if this cliff of the building has a height h like this here, then you can use the equation once again. Let's see. It's going to end up on the ground. It started at a height h above the ground. And now there's another particular case here. We'll suppose that it was thrown down so that the v naught y is not 0. So it was not just dropped down, but someone threw it down with some initial v. You'll have a minus v naught y times delta t minus a 1/2 g times the delta t squared. So in this case here, if you want to get delta t, you should be able to solve for it, get delta t equals some number. That again will be delta t sub hang time. You can get the hang time of the ball once again from this, but if you look very carefully what you formed here, you have once again a quadratic equation, which you have to solve for to get the roots, and one of the roots will be the hang time. So this quadratic equation comes from in particular because this term right here, the v naught delta t term, was not equal to 0 right here. Not equal to 0 because, as I mentioned just a second ago, the ball is actually thrown down, not just dropped. It wasn't just held from rest and dropped, so someone actually went up with their hand and gave it a throw down as it went. And because this term is not equal to 0, a quadratic equation is generated. Now, in the case here where, say, v naught y was 0, and this is where it's just simply dropped. Someone is just holding and then opens her hand and it falls. If v naught y was 0, then you will get a more simple equation to solve because you get 0. Still hits the ground. Still falls from height h above the ground, but now this term is 0 because vy is 0, but you still have the minus 1/2 g delta t squared term. So this can be solved for delta t very easily. You get some number for that, but this delta t here is still the hang time, which can be used. Let me just reiterate again. I showed you several different considerations. There's both linear and quadratic equations which pop up in this, but all we did was try to find a hang time by once again interpreting the y-coordinate action of the ball. Where did it start from? Where does it end up? Any velocities in there? We look purely at the y-coordinate for vertical. And there, we know there's x motion also. There can be x motion in these things, but we didn't look at that at all. Not for the hang time. Hang time comes from looking at the y-coordinate or the vertical component only.